Welcome to EE 544 on Tuesday, January 28th.
Good afternoon, everybody, and welcome to EE 544. First of all, before we continue our discussion aside, I received this question just to make sure that everybody is on the same side. How do we calculate the average power in a periodic waveform and also in the harmonics? I am sure that most of you know, but I just want to make sure that everybody and power in what? Power in harmonics. Yeah, can you zoom back please a little bit? Thank you. Okay, now the answer to that question is the following. Now, first of all, x of t is a periodic signal. It means I can represent it by what? The Fourier series Hn. Can I use omega naught here? I'm glad just to make things simple. Omega naught or omega c t n goes from minus infinity to infinity. That is a what? A periodic function, and the average power p. Average. This is the total average power. Total average power. It's what? It's the power in one period, which is what? 1 over t, the integral, minus t over 2 to t over 2. Does it have to be minus t over 2 to t over 2? Could it be from 0 to t? All what I need is one period, x squared of t dt. This is how you calculate the total average power. Clear? The total average power. Keep in mind, if x of t happens to be a pure sinusoid, then we already know what the total average power is. Is what? A square over what? Over 2. But the periodic signal does not have to be a what? Does not have to be a pure sinusoid. It could be a square one. Now, this units, by the way, units? Watts. This only gives you what? The total average power. If you want to break it into what? Contributions from the fundamental, from the second harmonic, and so on and so forth, what is this another way? This is equal to the summation of what? N goes from minus infinity to infinity, absolute value of x of n square. Did you understand that or not? Question. By the way, you don't understand what x of n is. X of n, where x of n is the what? The Fourier series coefficient, which is what? What is x of n? X of n is what? 1 over t integral minus t over 2 to t over 2 x of t times what? E to the minus j n omega naught t. Clear? Clear so far? Okay. Now, I think you did this on the homework, but I just need to make sure everybody gets it correct. Question number 1. Is this complex in general? This is complex. When you calculate the power, you only take the what? Absolute value. The phase does not get into the picture. Clear? Answer me the following question. What is the power in DC component? I'm still waiting. Is what? Absolute value of x of 0 square. Did you get it? Okay. What is the power in the second harmonic? A question. Is it possible that this one equal to 0? Why? When we don't have any what? Any DC component in the periodic signal. If you have a periodic signal like this, does it have a DC component? Does not have a DC component. Why? The negative and the positive will what? Cancel each other. But if I have this, do I have a DC component? Yes, I do have a DC component. Clear? Clear? Okay. What is the second harmonic? Still waiting. 2 times what? X of 2 square. Why 2? One more time. Why 2? You need to take the n and the what? The minus n. And the absolute values are the same. Remember, recall, x of n is equal to what? X of minus n conjugate. Which means when you take the absolute value, they are the same value. So you multiply by 2. Yes? Cannot hear you. If the question tells you what? It tells you how many components should you take to get 90% of the total average power. What do? You take what? This is, you calculate the average power, you multiply what? By 0.9 to get the 90%. Yes? And you keep adding what? You keep adding components until you get what? 90% of the total average power. That is referred to as what? The 90% bandwidth. Clear? Clear? And again, remember, the phase does not get into the picture. Yes or no? Okay, I received the email. I just want to make it. By the way, the TA should have shown you this in the first discussion session, but apparently he didn't. So anyway, clear? Any question on this? Yeah. Remember, by the way, when you talk about average power, we are talking about what? Periodic signals. Clear? Okay, good. Now, let's get back to our discussion. We started looking at the transceiver architectures, and we started looking at different components of the receiver. Let's go over them quickly. Antennas required, again, to convert electrical signal to electromagnetic signal. When you deal with antenna, the characteristic you need to worry about what? Operating frequency range. What is the range? Especially if you are using a multi-band, multi-standard type phones, where the bandwidth is going to be what? Extremely wide. You need to make sure that the antenna handle that wide range. The size of the antenna, this is physicality stuff. Clear? You should be able to what? To carry the mobile phone, for example, in your pocket. If you do have direct TV or a dish network, you need to use a what? A small dish. You don't want to use a big dish. And always keep remembering that the size of the antenna is inversely proportional to the what? To the wavelength. Clear? To the wavelength. Did I say inversely? I'm sorry. It is proportional to the what? To the wavelength. Clear? Not inversely. Proportional to the wavelength. So the higher the frequency, the wavelength will become what? Lower, which means the size of the antenna is smaller. Gain, again, as I told you, the gain is going to be dependent or proportional to the what? To the cross-sectional area divided by what? Lambda square. Are you following or not? So the smaller the lambda, the gain of the antenna is what? Is bigger, as we will see shortly. And then the pattern, of course, we could have what? Omnidirection in all directions, or it could be what? Directed to directional antenna. Directional antenna, most of the power will be what? Focused in one direction. Different types of antennas, smart antennas, and so on. We went through this from last time quickly. We went through filters, and we said that filters are what? Frequency selective devices. Frequency selective means what? If it is a low-pass filter, it will what? Allow low-frequency components to pass through, reject the highest one, and vice versa. So we have high-pass filter, band-pass filter, band-reject filter, all-pass filter, and so on and so forth. Again, as I told you, in our course, mostly we will be interested in the low-pass filter, which will occur in the baseband or in the back end, and in the band-pass filter, which will appear in the rest of the RF chain. Clear? And again, as I told you last time, the high-pass filter are not desirable because it has a what? It has a very large bandwidth. Remember, high-pass filter, what does it mean? It means that it will pass all the frequency components from F sub C, from the cutoff frequency, all the way to what? Infinity. Which means what? We know that the noise occupy what? A wide spectrum, a large noise power will go through a high-pass filter. High-pass filter is not a desirable filter. Filters are, remember, by the way, after a mixer, you have to have a what? Filter, because the mixer will generate what? Components that are undesirable. When you deal with filter characteristic specification, the bass band gain, the insertion loss, the out-of-band attenuation, the selectivity. Selectivity means what? The sharpness of the filter. We define the Q one more time. What is the Q? The Q is the what? Is the center frequency divided by what? The bandwidth of the filter. The center frequency divided by the bandwidth of the filter. And again, as I told you, this is measured either in dB per what? Octave, or dB per what? Decade. Decade means what? The frequencies are separated by what? By 10, multiples of 10, octave multiples of 2. Clear? Both of these are used in the literature or in the industry. So when you hear talk about dB octave, dB decade, don't be surprised. Amplifiers, again, as I told you, amplifiers are used both at the transmitter side and at the receiver side. The transmitter side is the one that we refer to it as a what? As a power amplifier, the purpose of which is to prepare the signal to have enough, sufficient power to cover what? To reach the distance, or to provide for coverage. Clear? To provide for coverage. That's the power amplifier. Now, keep in mind, as I told you last time, power amplifier consumes a lot of power, which means what? You need to switch it off when you what? When you are not sending. When you are not transmitting anything, that power amplifier does not need to be on. You just can shut it off. The receiver needs to be what? On. Because you never know when you are going to receive calls from the other side. At the receiver, we have a low noise amplifier. Again, as I told you last time, the purpose of the low noise amplifier is to provide for what? Amplification of the weak signal without addition of what? Substantial noise. You don't want to add substantial noise. You want to design your LNA to provide for what? Just an amplification of the signal. Clear? Okay, with some noise in there. We'll discuss this in detail. The IF amplifier, notes by the way, IF amplifier only if you are using a what? A multi-stage receiver. Clear? A multi-stage receiver. The IF amplifiers used at what? At the IF stage, both at the transmitter and the receiver. And again, as I told you, when you design your receiver, the gain, you are not going to put it all in what? In one amplifier. You are going to distribute it over a range of amplifiers across the receiver chain. By the way, is it possible we do have multiple IFs? Multiple IFs means what? IF1, IF2, and so on and so forth. We will talk about that in just a second. Clear? Now, amplifiers, unfortunately, are what? Are nonlinear devices. Nonlinear devices means what? Means they are going to create somewhat or generate some frequency components that are not available in the input. Clear? Now, the major thing that we need to remember when we deal with the amplifiers is that we need to look at the modulation types. If the modulation is what? Constant envelope, we are able to operate the amplifiers at what? Very near or at the saturation. Clear? But if the modulation techniques are of variable amplitude or variable envelope, the amplifier needs to be what? In a linear mode. We will see why shortly. The answer is that it will generate a lot of what? It will generate a lot of harmonic components, intermodulation components, and so on and so forth based on this thing here. The specifications of the amplifier, when you specify amplifier, the power gain, notice by the way, I did not say voltage gain. When you talk, RF people talk about what? Power gains. Digital people mostly talk about what? Voltage gain. Clear? RF people talk about power gain. The power gain of the amplifier, the noise figure, or sometimes they call it what? Noise factor. And noise figure is measured in dB. Noise factor is not in dB. And we will talk about that. But basically, the definition of the noise figure is the what? Is the ratio of the signal to noise power ratio at the input to the what? Signal to noise ratio at signal to noise ratio power at where? At the output, measured at what? Measured at room temperature. Now you might say, well, if it was not room temperature, that we will discuss it in detail. And that's the major problem people what? Make mistakes in. The reason that they specify the what? The room temperature, they did not, who's they? The people that are coming with what? With these definitions. Clear? The world radio conferences and so on and so forth. They wanted a definition for this, the signal, for the noise figure that is independent of what? Of the temperature. You just talk about noise figure at what? At room temperature. In other words, if somebody asks you what is the noise figure, you don't need to tell them what temperature are we talking about. The noise figure is measured at what? For room temperature. But we'll talk about that shortly. The nonlinear effects, the 1 dB compression, how did we define? The 1 dB compression is the value of the power in which the linear characteristic deviate from the what? Nonlinear characteristic by how much? By 1 dB. So you get a what? 1 dB compression. Clear? I will talk about that shortly. What does this determine? When we talk about the compression, what is this crucial in determining? This one is crucial in determining the non-linearity, the intermodulation components. Are you following or not? The selectivity of the signal, not the sensitivity. Did you get my point or not? Clear? The blocking, the blockers. We'll talk about it. It depends on what? The dB compression. Clear? On the other hand, the noise determine what? Determine the sensitivity. What is the weakest signal that can be detected? We refer to it as what? MDS. MDS stands for what? Minimum detectable signal. All of this, we will study it in detail. Harmonic distortion, keep in mind, harmonic distortion is what? Is you are generating frequencies that are what? Related to the fundamental by what? Integer multiples. Clear? Integer multiples. So for example, second harmonic, third harmonic, fourth harmonic. Let me ask you a question. If we do have two input signals to an amplifier, two input signals, so it's what? For example, A cosine omega naught t plus B cosine omega 2t, omega 1 and omega 2. Yes? Okay, and the amplifier is nonlinear. The amplifier is nonlinear. Will you get harmonics or will you only get intermodulation components? You will get both the harmonics and the what? Intermodulation components. Give me an example of the harmonics. When you do have a cosine, one term, the cosine, and you square it, you get what? Cosine squared. That's the second harmonic. Do you understand that or not? But to get the intermodulation components, you need at least how many signals at the input of the amplifier? You would need at least what? Two signals. With one signal, you are not going to get what? Intermodulation components. Clear? And again, as I told you, the intermodulation components is what? Plus or minus M, F1, plus or minus what? N, N, F2. Clear? Some intermodulation components will be what? Way outside the band of interest that can be filtered out very easily. Some of them will be located within the what? The band of interest. And that is a big what? That is a big headache. Which means what? I cannot filter it with the what? With the desired signal because they are occupying the same band. What I need to do is what? I filter it where? At the beginning. So by the time it gets to the what? Later stages of the amplifier, its effect will become what? Negligible, because its length has been, or its amplitude has been what? Reduced. We'll talk about that shortly. And then we talked about what? The intercept point. The intercept point. Intercept point is the point at which what? For example, third order or second order. Let's take the third order. This one is more important than this one. Third order intercept point is the value of the input power in which what? At which what? The output fundamental power will be equal to the what? The output third harmonic component power. Did I say third harmonic? I'm sorry. Third intermodulation component, not harmonic, sorry. Third intermodulation power. Clear? I will show you that shortly. And always remember, the larger the IIP is, the more what? Linear the device is. The more linear the device is. Okay. Then we start this quickly from last time. We started talking about mixers. Mixers, again, where are they used? Transmitter and what? Receive. Could we have more than one mixer? We could have more than one mixer. Remember, when we talk about what? Up conversion at the transmitter side. When we talk about up conversion and modulation, these could be what? Different. In other words, you could modulate and then what? Up convert. Or they could be what? The same. If they are the same, you are using what? One mixer to do the job. But if they are not the same, you are going to do what? Multiple mixers. Clear? A mixer has how many ports? 3 ports. What are the ports? The RF ports, the local oscillator ports, and the what? IF ports. Now, which one is the output depends on what? Whether you are at the transmitter side or at the receiver side. At the transmitter side, the inputs are what? Are the IF and the what? Local oscillator. The output is the RF. At the receiver side, it's the other way around. The RF and the local oscillator are inputs. The IF is the output. Clear? Okay. When you deal with mixers, again, ideally you are going to generate the what? The sum and the what? And the difference. Clear? The sum and the difference. Now, keep in mind, on the transmitter, we are interested in the what? In the sum, because it's up conversion. On the receiver, we are interested in the down conversion. Clear? Now, When we get to the mixer, we will see that they are either accomplished by a nonlinear device. Why does the device has to be nonlinear? You are generating new frequency components. When you are converting, for example, when you are converting from one frequency to a higher frequency, did you generate a new frequency component? That's the nonlinearity. Did you get this or not? A mixer needs to be a nonlinear device. The nonlinearity either from the device itself, or we can operate the mixer as a what? As a switch. On, off, on, off, on, off. When you do have on, off, on, off, on, off, what are you going to generate? You are going to generate the what? Second, third, fourth harmonic, and so on and so forth. Clear? We'll talk about that shortly. We understand the design of each one of them. What is the importance of the mixers? The important thing of the mixer is the first one, conversion loss. Question, is it possible that we get conversion gain? Conversion gain. Now, when we say loss, what are we talking about? Let's assume we are talking about the receiver. The loss is the ratio of what? The IF power divided by what? The RF power. Don't include the local oscillator in the picture. Did you understand what I just mumbled? At the receiver, the ratio of the IF power, which is the output of the mixer, divided by the RF power, which is the input to the mixer, is what is referred to as what? The conversion loss or conversion gain. If your mixer is a passive mixer, does not provide any gain, you are only going to get what? Conversion losses, which means this one is what? Everything in negative dB. Negative dB. Or the question will tell you what? For example, 3 dB loss. Conversion loss, which means what? Minus 3 dB. Did you get it? Okay. But could it have gain? Of course, it could have gain. And by the way, if it could have gain, that's good for us because part of the overall gain is what is going to come not only from the amplifiers, but it's also going to come from the mixers themselves. Clear? Okay. Now, the problem with the mixer is that they are not ideal. They are going to generate what? They are going to generate harmonics. Are you following? And they are going to generate harmonics. And even, as I will show you shortly, is the isolation issue. What does that mean is the following. Listen to me so that you understand what I'm talking about. This is the mixer. This is the RF. And this is the local oscillator. Now, think about our receiver. It's a what? Direct conversion receiver. We'll talk about that in a minute. Direct conversion, or what is known as what? Zero IF. Zero IF means what? You go all the way from the RF to the what? Baseline. If there is a leakage, by the way, which one is stronger? The local oscillator or the RF? Local oscillator is much stronger than the RF. Why? This is generated locally, whereas this one, it has been what? By the way, even though this one has been amplified,
the time is
what comes
18
in here
o'clock.
before the mixer? And so we have the what? For example, the LNA. Are you following me on that? So even though it was amplified, but it's still, this one is stronger. This one locally generated. If there is a leakage, listen to the leakage, from this port to this port, from the LO to the what? RF. What are you going to do? You are mixing the local oscillator with itself. Yes? What do you generate? Do you generate a DC signal? Why? The local oscillator is a what? Cosine omega naught t. Let's say. Mix it with yourself. Sorry, mix it with itself. Not yourself. Mix it with itself. I'm sorry. Mix it with itself. What do you get? You get cosine square omega naught t. You follow me or not? Cosine square omega naught t is what? 1/2 plus 1/2 cosine twice the angle. Cosine twice the angle, I don't care about. Why? Because the filters will what? Reject it. This is at the receiver chain. Clear? But the DC, is it important or not? It is important. Why? Because this is a direct conversion receiver and the baseband is centered around what? Around 0. So if there is a DC component in here, it means as if you are shifting what? You are shifting the spectrum up. Yes? Now you might say, okay, so shift up, can we shift it down? Put a capacitor? How do you block the DC? Put a capacitor. Are you following me or not? But putting a capacitor in series, it is equivalent to creating a low-pass filter. Do you agree? Do you agree? Why? Why? What is the impedance of the capacitor? The impedance of a capacitor is what? Is 1 over what? J omega C. Are you following me? So when you put, did I say you create a low-pass filter? I meant you create a high-pass filter, not a low-pass filter. If you put here, like this, a capacitor in series, will the DC go? Will low frequency components go? Why? Because the impedance of this guy is what? 1 over j omega c. At low frequency components, this one behaves as a what? Open circuit. Which means what? Low frequency components will not go through because it's behaving as a what? High pass filter. Yes or no? But if we are doing direct conversion, all of the baseband is what? It's low frequencies, which means what? You are going to distort it severely. Did you understand what I just said? Yes or no? We'll talk about that shortly. By the way, even worse is to what? Is to leak from here back to the input of the LNA and then what? Back again. Which means what? You are mixing yourself with a stronger version of who? Of yourself. Did you get this or not? One more time. Is there another problem you see? By the way, this problem is not crucial in super heterodyne receiver, because in super heterodyne receiver, this one is not the same as this frequency. Do you understand what I just said or not? Okay. Let's concentrate on the 0IF, which is direct conversion. Is it possible that this one, this signal, will leak all the way out to the antenna? To the antenna, which means what? You are transmitting. This is the receiver. You are going to be transmitting at what? At the same frequency that you are what? Receiving. Not sure. Is this the same as this? Indirect conversion. Is this the same as this? If this one leaks, which is what? High. I will show you all of this detail in a minute. This one high, it will leak all the way to the what? To the antenna. Clear? So we need to make sure that when you use mixers, you need to make sure that all of these ports are what? Properly isolated. At least 40 to 50 dB isolation. Do you understand what that means? 50 dB means what? Level is what? Going from this one that is going to be leaked in here is 50 dB below what? Below the actual level. Did you get this or not? I will show you that in just a second. Now, noise characteristics again of the mixers. Mixers, by the way, unlike the low noise amplifier, mixers are what? Noisy devices. Especially, by the way, if you are going to design them as what? As switches. Those switches, when they what? Open, close, open, close, open, close. That action will generate a lot of what? Impulse noise, impulse kind of noises. Did you get this or not? Okay, but we'll talk about that shortly. And of course, the isolation that I was just telling you about. Clear? Okay. Oscillators. Where are the oscillators? This is the local oscillator. This is an oscillator. Okay, question. Is the oscillator, does it have an input? Or it's self-driven? Self-driven. Does not have an input. Notice, by the way. Do I need an oscillator or do I need a synthesizer? It depends on the usage. A synthesizer is what? When I talk about synthesizer, it's a what? It's a variable what? Variable oscillator. Variable oscillator is what? A device that you can control what is the frequency that you are going to be generating. Clear? Okay. It could be a what? It could be a fixed oscillator, which means what? Generating only what? Generating only one frequency. Do we need oscillators in what? Transmitter, receiver, or both? We need both. Could we have more than one oscillator? As a transmitter, for example, remember I told you, you could do modulation and then what? Up conversion. These are two separate oscillators, as I will show you in just a second. Clear? Up and down and for modulation. What do you deal with oscillator? When you deal with oscillator, what are the parameters of interest? The first one is what? Is the tuning range. Remember, I told you, the VCO means what? Voltage controlled oscillator. The tuning range. From what range to what? To what range? Did you understand that or not? Remember, I told you in the mixer here. Did I speak, by the way, last time about whether the local oscillator in the mixer should be higher or lower than the RF? Did we talk about that? We refer to it as what? High injection and what? Low injection. Clear? And I told you what? It is easier to design an oscillator that has a what? That the ratio between the high to the low is what? Low rather than what? High. This is what is referred to as what? Tuning range. How about switching time? Switching time, you should be able to switch the oscillator from one frequency to what? Another frequency in a very short period of time. Did you get this or not? So we are going to be dealing with all of these. What in the world is a phase noise? Ideal oscillator. How does the spectrum look like? If you have an ideal oscillator and you connect it to a spectrum analyzer, Yes? How does it look like? It looks like this. This is F. What is this? I already talked about this before, but you are keep forgetting. S. What is this? Sx of F. The power spectral density. Units are what? Watts per hertz. Clear? How would it look like? An impulse. An impulse. Are you following me or not? At what frequency? At F sub C and minus what? F sub C. Clear? Does it look good? It looks really good. Is it? In reality, is it like this? It's not like this. What you are going to get in reality is a whole bunch of what? A whole bunch of what? Noise in there. Clear? It looks, when I sketch it, looks like Big Bird. You are not familiar with Big Bird. Okay, anyway, don't worry about it. That is what is known as what? That is what is known as phase noise. Now, you might say, so what is the problem? Just a phase noise. What is the problem with that? You have to remember, this one is going to be mixed with who? With the RF signal to what? Down converted, for example, to the IF. All of these will show up in where? In the IF also. Did you understand what I just said? We need to make sure that our oscillator is what? Is rather what? Very clean. Are you following me? Very clean. Clean is what means? By the way, could this FCC change it a little bit? Drift. This FCC, with the passage of time, could it drift? We need to what? We need to make sure that our oscillator is what? Is relatively what? Accurate. Especially with who? With temperature. Because as the temperature increases, you are going to see what? The frequencies is going to what? Change. Most widely used for accuracy is what? Is a crystal oscillator. The crystal oscillator. We'll talk about all of these things shortly. And of course, power consumption is also a major factor of this. Types of oscillators that we will be talking about is what? LC. We will talk about these and we will call them what? A tank. When you see a circuit that has what? L and C, that is referred to as a what? As a tank circuit. What can you tell me about these two components, the L and the C? Both of them are what? Lossless, ideally. Which means what? One of them stores magnetic energy, the other one stores what? Electrical energy. Yes or no? When one loses electrical energy, the other one will gain what? Magnetic energy. Yes or no? So the total will become what? Fixed. That results in what? The oscillation. Clear? However, what is the problem with this? The problem with this is that this L and this C are not what? Ideal. There is parasitic what? Parasitic resistance associated with them, which means what? It means that we are not guaranteed. If you look at the output, which is the oscillation, you will see with time it begins to what? It begins to decay. Are you following that? And we need to what? We need to build it up again. Clear? We need to build it up again. And we'll see how we do that shortly. And of course, LC is susceptible to what? Variations in the supply voltage and temperature and so on and so on. Crystal oscillator, on the other hand, is by the way, we will call it later on. I want you to get familiar with this. Anybody have seen this? What does this stand for? Temperature compensated crystal oscillator. But we'll talk about that shortly. Let's not worry about that. These are accurate. From these, by the way, we will generate what? By using divider circuits, multiplication circuits, we will derive multiple what? Multiple frequencies for what? For synchronizations, when I say synchronization, means what? Carrier sync, or what? Symbol syncs, and so on and so on. We are not going to use what? Multiple crystal oscillators. We will use one crystal oscillator, and we will use what is known as a what? Phase lock loop. PLL stands for what? Phase lock loop. We are going to what? Lock a local oscillator with the what? With the highly reliable. The reliability will what? Will translate to the local oscillator. Clear? And we will study this later on in detail. This is for the frequency synthesizer. Now, baseband processing. This one I will only give you an overview. This is the material of EE 536B. I have no idea why it was canceled this semester. I got upset when I saw it's canceled. But in any case, when we talk about baseband, baseband means what? at the back end of our receiver. What happens in here? By the way, could demodulation appear in here? Demodulation could appear in here. Are you following me on now? And most of the time it does. It is done in digital domain. Here you have all types of what? The synchronization stuff, the decoding, the encryption, decryption, and so on and so forth. The DAC, the ADC, and all of these issues that deals with what? That deals with the recovery of the baseband signal from the RF or from the IF stage in the case of the super heterodyne receiver. Clear? Now, here later on, I will just give you an overview about the design of the ADC and the DAC. This one is more problematic than this one. Clear? Because this one requires what? Requires sampling, requires quantization, and from the quantization, you are going to get what? Losses, and so on and so forth. Clear? But we'll talk about this briefly later on. Okay. Now, from the performance point of view, we talk about these, the most standards outline these test conditions on the noise factor or the noise figure, the intermodulation levels, the blocking performance. What does that mean? Blocking. Again, we'll get to it later and shortly in detail. Blocking means what? There exists a strong signal, not a desired signal. There is a transmitter that happens to be close to a what? A desired receiver. That transmitter is not the desired transmitter. It's some other transmitter. Where is the desired transmitter? The desired transmitter is far away from the what? From the desired receiver. Clear? That transmitter, the one that is close to the receiver, happens to generate a strong signal because it happens to be close at a frequency which is very close to the what? To the desired signal. Are you following on that? If that signal goes through the chain, it will result in what? It will result in a block, which means what? Your receiver is going to be what? Desensitized. What does desensitized mean? The word English. Desensitized means what? It loses any what? Sensitivity. Which means what? The signal is there. Which signal? The weak signal, but I will not be able to what? Sense it. Because the blocker has already what? Blinded me. Think about it this way. It blinded me, overwhelmed me. Did you understand what I just said? We say the receiver desensitized. Desensitized is what? Has no sensitivity whatsoever. And we will talk about that later on. Of course, the receiver sensitivity is required. Can you give me an example of a receiver sensitivity? For example, in GSM, GSM stands for what? The Global System for Mobile Communications, second generation. The receiver sensitivity could reach what? Minus 100 dBm. Remember, dBm means what? dB milliwatt. Is that a high power or very low power? Very low power. Are you following me or not? Now, remember, what did we call the dynamic range? The dynamic range, which units receiver dynamic range? Is it dBm? Receiver sensitivity is in what? Dynamic range, dBm or in dB? dB. Oh, how did we define it? The dynamic range is the what? Is the power of the highest frequency, is the strongest power that can be what? That can be received minus what? The lowest power. When I say the stronger power can be received without what? Without blocking your receiver. Without blocking your receiver. When we talk about dynamic range, means what? The receiver is still operational. Clear? Who determines, one more time, who determines the highest power? The nonlinearity characteristics of the what? Of the receiver. Who determines the lower one? The noise characteristic. Are you following? The noise will have an effect on what? On the sensitivity. And we will study all of these in detail. Transmitter power output, that's the level. Clear? And the power or the crest factor, the power, how did we define the power? Is the power, what does it stand for? The peak to average power ratio. Peak to average power ratio. The crest is what? Is the root mean square stuff. Clear? Okay. All of these are used, especially the power. And we need to see how we can calculate it for different type of modulation technique. We'll get to it. The higher the power, what does it mean? It's an indication that the modulation is constant envelope or non-constant envelope? Non-constant envelope. Are you following that? Because remember, the peak power depends on what? The amplitude, the peak amplitude. Clear? And if the amplitude is fixed, then the power The peak and the average is what? It's the same. But if the amplitude is what? It's non-constant envelope, we will have what? Peak power and what? Average power. So we need to understand that. Okay. And of course, the other aspects of the design of your transmitter is what? Is the emission profile. This is what we refer to as what? As the mask, the emission mask. All of your transmission, the emission, the power spectral density needs to be confined within the what? Within the mask. And I will show you shortly different type of mask for different standards. Clear? So that you can see. This is, by the way, this is the front end. By the way, you notice when you are transmitting, what is this? What is this? This is the high power, because there was what? There was no propagation yet. These are the side bands. Are you following or not? Notice, by the way, the side bands are what? Are filtered out severely because you want to confine your emission within the band of interest. Look at what you receive. Tell me what you are receiving. This is what you are receiving. Yes? Where is the desired power? This is desired power. What are these? These interferers, what? Interferers in the nearby. Will this one eat those alive? Think about it this way. Think about it this way. Who will win if they fight? If they fight, who will win? This one will beat this one. Are you following me or not? Somehow you need to be able to what? To sense this channel and to what? Select it. Clear, select it, and reject all of these things. Clear? Okay, but we'll talk about that shortly. Now, let's start with the transmitter first of all, and start with the issues involved in the transmitter. The functions of the transmitter is what? Modulation, frequency conversion, and what? Amplification. By the way, part of the amplification is what? Is impedance matching also. Keep that in mind. You need to make sure that the output of the power amplifier is matched to the antenna. Otherwise, as we'll see shortly, there will be a lot of power reflected back. Reflected back means what? Waste of power. Clear? Okay. So one more time. The primary function of transmitter, modulation, up conversion, frequency conversion. Could this one be done in the same way? It could be done, but not necessarily. Modulate, frequency conversion, and what? And amplification. The key parameters, again, the spectral purity. What does this mean? Tell me, what does the spectral purity mean? Remember what I showed you a moment ago, the local oscillator? When we say your local oscillator is pure, what does it mean? It has just a single delta. If it is not pure, then it will have all of these phase noise along with it. Generates what is known as a spur. What is a spur? When you hear the word spur, or you call it what? A spurier emission or components. There is a U here. Spurier components. What is a spur? Very simple definition. An unwanted signal. We call it a what? A spur. But do not confuse it with the noise. The noise is not regarded as a what? As a signal. Clear? The noise is just a random phenomenon. Clear? The word spur, don't worry about it right now. We'll talk about it in detail. When you hear the word spur, this is the first time you hear it? Is this the first time you hear it? Okay, so right now you know, when you hear spurious emission or when you hear the word spur, is an unwanted signal. Where did this unwanted signal came from? From the what? Imperfect characteristics of the local oscillator, from the nonlinearity, and so on. So all of these are referred to as a what? As a spur. Clear? An unwanted signal. Okay. So the spectral purity, the output power, modulation accuracy. What is that all about? The I, modulation accuracy, the I and the Q. What does I stand for? In channel, Q, quadrature. We'll talk about this in detail shortly when we get to the modulation. But let me explain it to you. The I and the Q are supposed to be what? Orthogonal. Yes or no? One is a cosine, the other one is a what? A sine. But if they are what? If they are not balanced well, in other words, remember the local oscillator is generating what? Cosine omega naught. Here, that is the local oscillator generating what? Cosine omega naught t. When you are going to apply it to a what? 90 degree, what are you getting? Sine. But that is only theoretical. If this one, by the way, what will happen? The cosine then will have the what? This is the I, this is the what? This is the Q. This will be multiplied by what? Cosine. This will be multiplied by what? Sine. Huh? Sorry. Yeah. Yes? What do I mean by IQ accuracy? This branch is supposed to be only the what? The I channel, which means what? The Q channel, if it goes in here, it should be equal to what? 0. Are you following me or not? It should be equal to 0. Did you get my point or not? Why? Because it's cosine and sine. When you integrate, it becomes what? 0. But if they are not accurate enough, if there is what? Phase shift between them, if the amplitude variable, some of the Q channel will appear what? In the I channel, and some of the I bits will appear in the what? In the Q channel. Clear? This is what we refer to as what? Crosstalk between what? The I and the what? The Q. We shouldn't do that. Are you following me or not? Doing this, as we will see later on, not now, doing this IQ modulation in the digital domain or in the baseband domain, in other words, at lower frequencies, gives you better performance than doing it in the what? In the RF, as far as the accuracy is concerned. Do you understand? As far as the crosstalk is concerned. And that is why we will see later on that most of the time the IQ is done where? In the digital domain. Actually, it is done in digital, which means what? This one is not generating what? Cosine omega naught t. It's generating samples of what? Cosine omega naught t. It's done in digital domain. Did you get this or not? But we'll talk about that later on. Clear so far? Clear so far? Okay, good. So, the transmitters are less complicated than the receivers. Why are they less complicated? Because we don't deal with what? We don't deal with all of these interference and so on and so forth, noise and stuff like that. We are still at the interface. But still, we need to worry about what? By the way, do we worry about band selection at the transmitter side? In other words, do we need, I'm not sure, did you get my point? In the transmitter, you are transmitting at a single what? At a single frequency. Where at the receiver, you need to have what? You need to have variable local oscillator to what? To select a given what? A given channel of your choice. Whereas this one, you are only generating what? One frequency. Are you following me or not? Cannot hear you. So this thing, what I meant by what? Only one channel will be what? Will be up converted. The power level, again, is deterministic. However, high DC power consumption. Clear? Notice, by the way, this is, when I say deterministic here, when you deal with CDMA, CDMA stands for what? Code division multiple access, because you are transmitting and you are transmitting at the same frequency and at the same time, your power needs to what? Needs to be dynamic, needs to be adjustable. Are you following on that? You need to have a power control mechanism so that when you are close to the what? To the desired receiver, you need to lower your what? You need to lower your power. When you are far away, you need to what? Increase the power. Clear? So the power is what? It's not deterministic like I'm showing it here. Clear? Yes or no? The receiver, is the power deterministic or is the power random? Received power. Of course it's random. It's going to go through what? This multipath and fading that we talked about earlier. Are you following? It's going to be fluctuating. Okay. Now, adjacent channel interference at the what? ACI stands for what? Adjacent channel interference. The bandwidth of the signal, again, is limited to the desired channel before it reaches the what? The power amplifier. We need, in other words, before the power amplifier, do we need filtering? You lost me here. Once you do not answer me, it means what? You lost me. Let's take an example. Let's take an example. You lost me. I can tell you lost me. Okay. Let's take an example. This is a super heterodyne transmitter. A super heterodyne transmitter. When you hear the word super heterodyne, what does it mean? You are going to go through what? 2 stages. Or more than what? 2 stages. What do I have? This is the information signal. A baseband signal. Think about this as a what? As a serial to what? Parallel conversion. Clear? Question. This I and the Q, does it need to come from the same stream or could it be separate stream? It could be separate stream. If you want separate stream, it could be separate stream. Or it could be from the same stream and using what? A parallel to serial converter. This is the DAC. What is the DAC? Digital to analog conversion. The point, what is the purpose of this? These signals are what? Are digital. Yes? Do they have sharp edges? They have sharp edges. I need to what? Smooth the edges so that it does not, I don't generate all of these what? Side lobes, the sink type. Did you get my point or not? So I use a DAC to smooth all of these edges. Clear? This is what we are going to refer. This is a combination of this one and this one. We will call it a what? We will call it the pulse shaping filter. Clear? Pulse shaping filter. This is this low pass filter, low pass filter. This is a local oscillator generating at what frequency? Single frequency. Is this a variable oscillator or a fixed oscillator? Fixed oscillator generating at the carrier frequency, whatever it is. Clear? Okay, but notice what I'm saying. This is not the radiated frequency. Clear? This one here, when combined with this, is going to generate what? In other words, what is this one is doing? Modulation or the up conversion? That's the modulation. The up conversion is this one. Did you get my point or not? So this one is doing the modulation. Again, the IQ, you add it. What is this all about? What is this one is doing? This one is doing the what? Harmonic rejection. Because from the mixer, you are going to get what? You are going to get, it's not an ideal device. You are going to get all types of harmonic. This one rejected. What is this one is doing? This one is doing the what? The up conversion. Yes? Okay. Assume it's ideal. Assume it's ideal. It's generating the sum and the difference. Yes? What is this one doing? Channel select. If you are only going to choose the what? Select the sum rather than the difference. That's the channel select. Clear? Clear? Question. Tunable or not tunable? Why? Why tunable? Why? It's a fixed frequency. Are you following that? By the way, you see a straight line, you see an arrow here. There you don't see an arrow here. It's not a tunable. Designing a filter. This is a filter, bandpass filter. That is not tunable. Is easier or harder than designing one that is tunable? The one that is not tunable, of course, it's easier. Clear so far? Clear so far? Okay. Now, what do I have here? Now, what is this? This one got rid of, this one supposedly got rid of what? The adjacent channels. Did you understand that or not? The adjacent channels are so the bandwidth of the signal is limited to desired sound before it reaches the power amplifier. Here comes the power amplifier. Yes? Let me finish the sentence. Let me finish the sentence. Come to the power amplifier. Is it non-linear? Which means what? It means that in the output you are going to what? Recreate those channels that you what? Recreate those that you have what? That you have gotten rid of. Are you following me or not? You recreate them because of the non-linearity of the power amplifier. Now you might tell me, okay, Professor, can I put a filter in here? But putting a filter in here will result in what? Insertion losses, which means what? You are going to lose. What are you going to lose? You are going to lose the power that was achieved by what? By the power amplifier stuff. So it's a dilemma. And that's why we need to make sure that the power amplifier is designed properly. Question? Whatever you decide. For example, if you were assigned a specific frequency, that's the frequency that you are using. Only on that channel. So for example, let me finish this thing. For example, assume this, give me an FM channel. Give me an FM channel. It's what, say that again? 105.9. What is that? Heavy metal stuff? What is it? Oh, rap. It's no wonder I don't know about it. Why? I have no idea what they are talking about. 105.9. Yes? Yeah? That's the frequency. That's the frequency you are going to be transmitting with in the FM broadcasting. Are you following me or not? In the FM broadcasting. Now, in a mobile thing, that's different. Because when you are making a call, every time you might be assigned a what? A different frequency. Yes? Which means what? Your transmitter needs to be what? Tunable within what? Within that range. Yes? Here we are talking about what? Just one frequency. You are transmitting at a single frequency. You don't need this one to be what? Tunable. Did you get my point? Did you get my point? If you are transmitting for FM broadcasting, that's one frequency, then it needs to be that way. But if it is tunable, then you need to what? Select the frequency, yes, and reject all the adjacent channels. Clear? Okay. The output of the power amplifier has to be what? Has to be matched to the antenna. Matched to the antenna means what? Means that we will see what matching means. Matching means what? Means that the load impedance and the output impedance of the power amplifier needs to be what? The conjugate, complex conjugate of what? Of each other. Clear? Otherwise, some power will be what? Reflected back, which means what? It's not going to radiate. Clear? This is a super heterodyne. Now we'll get to it in a minute. I want to show you, and we'll get back to the charts that we missed. Let's look at the direct conversion. Direct conversion means what? Directly. Let's see. This is the baseband. Yes? Okay. Then it goes what? The DAC and the low pass filter. This is the pulse shaping. Answer me the following question. This frequency, F sub A, is it the carrier frequency? That is the carrier frequency. That is the carrier frequency, which means what? This is the modulation and the what? And the up conversion in one step. Clear? You are adding the what? You are adding this, by the way, in here, missing in here, at the output of the power amplifier, you need a what? You need a filter to reject or to make sure that the channel is what? Is within the selected channel is the one that is chosen. Clear? And then the power amplifier and the matching filter. Which one is easier? I want you to see this, and I want you to see this. Which one is easier? This one is definitely what? It's definitely easier. Clear? However, I want you to understand one thing here, and we will see this. Let me see. Okay, let me show you. I'm not going in order. I'm sorry, but I will show it to you as we move along. This is the direct conversion. Yes? I want you to tell me the frequency in here at the output of the power amplifier. Is it the same as the local oscillator? This frequency that is radiated, is it the same as the local oscillator? Now, I want you to understand one thing here. Assume this is an ideal local oscillator. Ideal, which means what? Pure. So it has a what? An impulse centered at what? At sub C. Yes? At the output of the power amplifier, which is what? Which is stronger than this signal. Did you understand what I just said? It's stronger than this signal. Why? Because it has gone through what? Through the power amplifier. And remember, in here, we don't have degradation yet. Why? Because the signal has not been transmitted yet. So we don't worry about fading and stuff like that. Yes? Is it at the same frequency? But is it pure? It's not pure. This is the modulated signal. Are you following me on that? But it is at the same frequency. If these components are not isolated well, there will be what? Leakage from here and even from here. Are you following me on that? Leakage all the way to the what? Local oscillator. Did you understand what I just said or not? This is what is known as injection. Is it written here somewhere? No. Injection locking. Injection locking. What does injection locking mean? Means this is so strong that the output of the local oscillator will lock. Lock means what? Synchronize with the signal. Do you understand that or not? We have what is known as injection blocking, and the other type is injection. These terminologies, you will hear about them only in the RF industry. Are you following me on that? In other words, if you open a textbook or something, you might not see this. Did you get my point on that? So some words, I want you to always remember them, because people in the industry expect you to know these things. Clear? Okay. So for example, in the local oscillator, when we say higher or lower, we call it what? High injection, low injection. This means what? Whether the local oscillator is higher than the RF or what? Lower than the RF. This one is different. We call it what? Injection locking or injection tracking. Which one do you think, by the way, is worse? Injection locking or injection tracking? Locking is worse. Tracking means what? Means all of these noisy in here, noisy oscillator, this one will try to lock it, will try to what? Mimic it. It reaches a point in which this one will what? Lock into this. Lock means what? It becomes exactly the same thing. Whatever in here will be in here. Did you get this or not? Cannot hear you. Do we have a problem in the, oh sorry, wrong chart. Do we have a problem in the super heterodyne receiver? This problem, the one that I just told you. Why? Because the radiated frequency is not the same as what? The local oscillator. Did you get my point or not? It's not the same as the local oscillator in this case here. Clear? So what I'm trying to tell you is that even though you see what? You see, this is again, injection pulling or injection tracking. Sometimes we call suffers from injection pulling or tracking. 1 second, please. Tracking or injection locking disturbance of the local oscillator by the power amplifier. Keep in mind, the power amplifier is what? It's modulated. It's not a pure thing. Clear? Question?
Yeah, could you please explain how the leakage occurs?
Those components, all of these components, are they on the same board? Are on the same board. So those wires are coming what? Very close to each other. You will have what? Induction, leakage from what? You put two wires at parallel to each other, very close to each other. Yes? By the way, some of them, if they are what? If they are fabricated on the same substrate, it means what? They are sharing the same substrate. There will be somewhat leakage from one to the other and so on. So all of these p-n junction, those p-n junction, there will be what? There will be leakage current going through. You agree with me or not? When you say, for example, when you do have a p-n junction and you say reverse bias, if the junction is reverse bias, there should not be any current in there. Yes? Yes? But when you say reverse bias, there will always be what? Small current, even though it's small current, but there will always be small current that will what? That will leak into that. Clear? Remember, by the way, capacitance, parasitic capacitance is all over the place. Are you following me or not? Okay, good. So keep that in mind. Now, so you need to what? You need to make sure that the local oscillator is well shielded. So the bandpass filter, by the way, what is this one is doing? One more time. The bandpass filter is suppressing harmonics. Modulation, by the way, if you are using simple modulation, for example, QPSK, can be done in the what? Using the same process. In other words, this whole thing, you done it in what? QPSK or MPSK or just any other type of modulation. Up conversion in one step. I and the Q must be what? Symmetrical. Otherwise, what are we going to have? Crosstalk. Which means what? The I channel will what? Some parts of the I channel will what? Leak to the Q channel and vice versa. Detailed, by the way, when we get to the modulation chart. I will show it to you analytically also. Clear? Clear? Okay. So but it is much easier to do the what? The IQ in the what? In the lower frequencies rather than what? In the higher frequency. And here, what are we doing it? We are doing it at RF. Yes or no? Keep that in mind. This is the comprehension. Now, one possibility to prevent the injection pulling or the injection locking is to do this. Let's see if you can help me here. What did we do here? Those are the what? The VCOs. Instead of using what? Instead of using one local oscillator at a what? At a constant frequency, which is the frequency of desire. Yes? We use what? Two VCOs. Yes or no? Such that either the what? The sum or the difference is the one that is what? The desired RF. Did you lose me? You lost me?
No.
Okay. This one is what? It's some frequency. Let's assume this one is F1 and this one is F2. I'm going to mix them. Remember, when you mix them, what do you get? You get the sum or the difference. Yes? Let's assume that you decided what? You decided that you are going to do the sum. What is the carrier frequency? If you use the sum, what is the carrier frequency? It's F1 plus what? F2. Now, is it possible that it will leak all the way to the oscillator? It is, but does it have any effect? Why? Because the local oscillators at the frequencies of what? F1 and what? F2, which are what? Far away from what? F1 plus F2. Did you get it? Okay, but on what expense? On the expense that I'm using what? Two local oscillator in this case. Did you get this? This is, oh, by the way, is this is this direct conversion? That is direct conversion. Are you following on that? That's direct conversion. But the carrier is different than what? Than each one of these VCOs. Clear? Each one of these VCOs is not the same. So it will not have any effect. Now, before we get to the receiver, can we get back to see the other issues about the transmitter that we might have missed? Nonlinearity, again, causes what? Causes intermodulation distortion. Clear? Intermodulation components may not be completely removed by what? Filtering. Might not be removed completely by filtering because they might what? They might overlap with the desired channel, which I'll show you in just a second. Modulation techniques, again, the constant envelope, example, FM, GMSK, GSM, all of these are what? Are what is referred to as what? Power efficient. Why? Because they are constant envelope. Remember when I told you about QPSK, I told you even though the signal points are on a circle, but at the point where the symbols are going to be what? Transitioning from one to the other, the amplitude might go through what? 0, for example, which means what? For a short period of time, the amplitude will what? Change, and it might even reach what? 0 as it passes through the origin. We will see when we get to the modulation source shortly, we will see that in GMSK or FM, they are going to go around the what? Circle. They are not going to go directly to what? From what? Phase 0 to what? Phase by. We call the what? Continuous phase shift gain. Continuous phase shift gain means what? Means the phase is going to change what? Continuously rather than what? Abruptly. Abruptly means what? Going from 0 to 180. Did you get it or not? Yes, but we'll talk about that later on. The constant envelope are what? Power efficient. Why? Because you are going to be utilizing the power, the amplifier, and it's what? Maximum efficiency possible. By the way, if you think the power amplifier maximum efficiency is 100%, think again. Are you following? Even the maximum efficiency might reach what? Those fancy power amplifiers might reach what? 60 or 70%. Where is the rest? What happened to the rest? The rest will go into heat. Are you following? It will dissipate. Do you understand that or not? Consume power. Okay. Now, but they occupy what? Larger bandwidth. These types of modulation technique, they occupy larger bandwidth, which means what? The bandwidth efficiency. What is RB over W? Bandwidth efficiency measured in what? Bits per second per hertz. Will it be high or will it be low? It will be what? It will be low. Are you following that? It will be relatively what? Low. On the other hand, the non-constant envelope, which means what? AM, PSK, QAM, all of these are what? Non-constant envelopes. Yes? In this case here, the power is what? They are power inefficient. Are you following? Why? Because we need to what? We need to back off. We need to back off from the what? The maximum power at what saturation? We call it what? The back off. Back off power to reach what? The linearity. But they are what? Spectral efficient. Which means what? It will result in what? High RB over W. High RB over W. Which means what? On a given bandwidth, we can transmit at what? We can transmit more bits per second. We can transmit faster. Clear? Okay. But we'll talk about that later on when we get to the module. We already went through this, all of this subsystems in the transmitter. Architecture, I just showed you. The super heterodyne, the direct conversion, and the what? The offset. Clear? Clear? Okay. Now, when we are going to deal with the design later on this semester, when we deal with design, circuit design, we are only going to be looking at what? The power amplifier and the what? Matching circuits. Do you understand? Matching networks. Clear? Clear? Now, again, as I told you, most RF classes, when they reach the power amplifier, they say what? It's time, we run out of time. They leave the power amplifier till the end. We will not leave the power amplifier till the end. We will discuss it in detail. So brace yourself. Okay, now, receiver. Why is it more complicated than the transmitter? One more time. Why is it more complicated than the transmitter? It is more complicated because the received power is so what? It's so weak. Are you following me? It's more complicated than the receiver. Mainly, it's a weak power in the presence of what? Noise, and in the presence of what? Interference. And the interference could be what? Stronger. Are you following me on that? This interference, again, could be adjacent channel interference, or it could be what? Co-channel interference. When we say co-channel interference, means what? The same frequency. Are you following me on that? The same frequency. This one, by the way, you cannot get rid of it at all. You cannot get rid of it. You are just hoping that the co-channel interferer happens to be a little bit what? Spatially, physically, or spatially separated than you, so that its signal will what? Will degrade. Clear? Otherwise, what do you do with it? It's the same frequency. You try to filter it, you filter your signal. Clear? No response. Clear? Okay, good. So it's much more complicated than the transmitter. Main function, demodulation. Of course, the main function is demodulation, getting rid of the carrier, demodulation of the desired signal, which happens to be weak in the presence of strong signals. Due to several scenarios of varying attenuation, the receiver has to have a wide dynamic range. What does that mean? Explain it to me. Is the power received, is it constant or variable? The receiver should be able to what? To deal with that range. When the received signal is strong and when the received signal is what? Weak. By the way, is it possible that the received signal is strong? When? When the transmitter happens to be what? Close to the receiver. The received signal will be strong. Clear? Clear? Okay. So the receiver has to have a wide dynamic range to be able to detect signals with different power levels and different, of course, data rates. Dynamic range, as I told you, determined by noise at the lower bound and by what? The nonlinearity at the upper bound. Clear? Okay. And we will talk about that shortly. Blockers, before we get to the design. Blockers, I already explained it to you. These are what? Large interfering signals. When I say large, what does it mean? High what? High power. Large interfering signals, referred to as blockers. This situation arises when you try to receive a weak signal from a distance transmitter in the presence of a strong nearby transmitter of an adjacent power, of an adjacent channel. Clear? Now you might say it is an adjacent channel, so what do I worry about it? I want you to see these diagrams so that you get my point. This is the desired what? Desired channel. Yes? This is F. Weak or strong? Actually, I should have sketched it even smaller. Are you following or not? Weak or is strong? Let's assume that it's weak. This is an adjacent channel. It happens to have a what? Stronger. Yes? Which means what? The power, total power is what? Strong. Even though the interference will not be what? At the same frequency. It will only be at what? The adjacent. Yes? But it's still, I wanted to see what happens here. Do you see this? Is this a relatively strong interference? So even though it's a side lobe, but because the main lobe was what? Higher, the side lobes will have a what? Will have a level of power that will damage the desired channel. I'm not sure, did you get the idea? Did you get the idea here? Yes? Even though this one is at an adjacent channel, but the side lobes might be even stronger than what? Than the desired channel, the main lobe of the desired channel. Clear? Okay. So this situation arises when you try to receive a weak signal from a distance transmitter. Interfering signal could be 50 to 70 dB more than the desired channel. 50 to 70 dB more. High or low? It's relatively high. Clear? Okay, resulting in overloading the front end of your receiver, driving it into what? The nonlinear region. Notice, by the way, one more time, the amplifier, when it goes through the nonlinear region, eventually it might become what? Compression. In other words, it does not provide amplification. It provides what? Compression. And if the signal is weak, we say what? We say that the receiver will not be able to sense that signal. Okay, so increasing the noise floor and so on and so forth. Desired signal is what? Is block. Clear? Clear? Okay. Now, power consumption, again, if there is no active communications, taking place, receivers needs to be in which mode? In the standby mode. Are you following me? In the standby mode, it cannot be what? Turned off completely. Why? You turned off completely, you have no idea when somebody will what? Will be calling you. Are you following me? Or will not be. But you what? You reduce it just to be able to detect if there is a what? If there is a transmission of a signal requesting some kind of data transmission. Power, DC power must be reduced during the standby mode so that you what? Conserve the lifetime of the battery. Clear? Clear? This is unlike the transmitter. A transmitter can be completely shut down. Okay. Receiver architecture that we are going to be studying. We are going to be looking at the conventional super heterodyne, direct zero IF receiver, low IF single conversion receiver, wideband IF, double conversion receiver, and of course I will give you an overview about the software-defined radio and so on and so forth. Clear? Okay. Let's start with the what? Let's start with the super heterodyne receiver. Let's start with the super heterodyne receiver. The received signal, yes, goes through what? Goes through a band select filter. Question one more time. Question. Is this the channel select or is it the band select? That's the band select, which means what? In addition to the desired channel, are all other channels will pass through. What will not pass through? Out of band channels. Are you following or not? Out of band channel. Some channel are all the Arab channels in the air? All the Arab channels in the air. Clear? Okay. So this is the band select filter. It goes through a low noise amplifier. I'll explain that to you in just a second. The AGC stands for what? Automatic gain control. Automatic gain control. And we'll study this later on in the semester. What is this all about? One more time. Did we talk about this before or not? I'll show you details next time. But let's go over it quickly.
Professor, we have 5 minutes left.
Thank you very much. Image reject filter. What does that mean? Remember, I have a what? Let me see if I have. I want you to see this. Let's see. This is the desired frequency. Do you see this desired frequency? Yes? I'm going to mix it. The mixer, the local oscillator, by the way, what does this arrow mean? A variable local oscillator. Why? Because the IF signal at the output is going to be what? Fixed. The desired channel is going to be what? Changing. Yes? Now, if the local oscillator is greater than the desired channel, yes? There could be another channel, yes, which is what? Higher than the local oscillator, separated from the local oscillator by how much? By the same value, which is what? IF. In other words, what do I have? I'm running out of time. Next time I'll show it you. Concentrate, concentrate. I have the local oscillator here, the desired channel here, the what? Image here. What is from here to here? That's the IF. What is it from here to here? IF. Did you get my point or not? That is called the what? The image reject filter. Image reject filter. Clear? Trying to reject this one here. Now, let me ask you a question here. What is the major issue here? If you decide that the IF, the value of the IF is large, what does that imply? What does that imply? Does it imply that this image will be rejected severely? Let me rephrase the question. Does this filter needs to be a high Q filter? You lost me here. Once you cannot answer me, it means what? You lost me. Do not lose me. Concentrate. What is the difference between the image and the center? And between the center and the desired IF. If you make IF large, which means what? This is here and this is here. This filter, does it need to be sharp filter or does not need to be sharp filter to get rid of the image? Does not need to be sharp filter to get rid of the image. Why? Because the image happens to be what? Far away. But in using a what? A not so sharp filter, what does that mean? It means other interferers which are in band, not out of band. Out of band already what? Rejected. Those interferers which are in band will go through the what? Not so what? Not so sharp filter. Yes? Which means what? When I want to select the desired channel, this one needs to be what? Very sharp to get rid of the what? The interference. Yes or no? Okay. How about if I make IF small? I mean, this IF value is small. Do I need to be sharp or not sharp? Sharp. Why? Because I want to get rid of what? The image. And the image needs to be what? Because IF is small, it means what? It's close. I need to be what? I need to make sure that the filter, I need to be the what? Sharp. But if I use a sharp filter, does this one needs to be sharp? This one does not need to be sharp. Why? Because the sharpness of this will get rid of what? A lot of interferers which are what? In band. Did you get this or not? In addition to the what? In addition to the image. Clear? Clear? Okay. One more question before I run out of time. Do we have a problem with the image in the direct conversion receiver? In the direct, jump with me. This is don't run out of time on me. Do we have an image here? This is direct conversion. Do we have an image problem here? Why? Why? Because in here, the local oscillator is the same as what? The desired channel. Are you following or not? So I don't worry about what? I don't want about the image. Did you understand what I just said? Yes or no? Okay, but I think I ran out. Did I run out of time? No response. Keep it quiet. Quiet. Okay. No. So the components of super 100 band select is going to reject out of band interference and noise. The low noise amplifier again provide amplification for all in-band channels. You see this one? The low noise amplifier provides amplification for all what? In-band channels. Why? Because the desired channel has not been selected yet. You only selected what? The band. So it will provide amplification for all of them, while reducing the noise effect of subsequent systems. When we deal with the noise analysis, we will see that it is the low noise amplifier that will govern the noise characteristics of the entire system. Which means what? Even if the subsequent stages of your receiver are noisy, if you can make sure that your low noise amplifier is what? With a very small noise figure, all the effects of the other noises will be negligible. Do you follow me or not? Okay. A high Q, which is sometimes off. By the way, why do I say high Q? Sometimes you need to design it off chip. Why? A high Q means what? The order of the filter is what? Very high, which means you are going to use what? Bulky inductors and bulky capacitors. Yes? You will not be able to what? To integrate it within the chip. You need to do it outside of the chip. And when you do it outside of the chip, you need to go what? Extend the wire from what? From the chip to the outside and then back to the what? Inside. Those wires are going to introduce what? A lot of problems in terms of what? Parasitic capacitance and so on and so on. So a high Q filter to reject the image frequency and prevent it from superimposing it into the desired channel in the IF. Let me ask a question before I run out. Let me ask a question. Does the image, if there is an image and you don't get rid of it, will it be down converted to the same IF? Will it be down converted to the same IF? It will convert it to the same IF, which means what? If you do not remove it before, when you down convert it to the IF, it's too what? Too late. You understand what too late means? Yes or no?
The time is
it's too late.
o'clock.
It will become part of the what? Part of the desired IF. You cannot. So you better what? You better reject it before at the end. Clear? Okay. So the entire RF, again, the entire RF down is down converted to what? IF using a VCO driven by a what? Who is driving this VCO? By a frequency synthesizer. Clear? By a frequency synthesizer. A high Q again, usually off chip, is also desired to what? Select the desired channel at the output of what? At the output of the mixer. Clear? Okay. Did I run out of time over?
Yes, we are out of time.
Okay, okay. See, I'm considerate. I asked. But we'll continue this next time. I go as fast as possible, but still. Are you following me so far? Yes. Okay, good.
This concludes today's session of EE 544 on Tuesday, January 28th, 2014.